Okay, guys, let's go through our last physics lesson. We're going to end here at 8.5. Like I said, there's a couple more sections left in here, but they are also very short and very theory-based. So if you want to take a read through them, that is totally up to you. I'll put this lesson posted on Monday. I'll also post your last summative assessment probably Monday afternoon, maybe Tuesday morning. And as soon as you are done it, you are done everything for Physics 30 that I'm asking of you. So hopefully you've done your lessons 8.1 to 8.4 already from last week. And then last one here, 8.5, is just an introduction. And all of these are just introductory lessons into ideas. So we're learning an introductory lesson into what is fission and what is fusion. So first we just kind of have to, basically the outcome is asking us to like understand the difference between them and the basic processes and reaction mechanism for each. So we'll start with fission. So nuclear fission occurs whenever a large nucleus, so in the example here they're talking about uranium, is split into two daughter nuclei. So in this example it's split into barium and krypton through colliding with a neutron. So the actual reaction that's happening is the neutron comes in, collides with a large nucleus, so something really big, heavy. Whenever I'm saying heavy, I'm saying like very high, like atomic mass associated with it. And we're typically talking about like a radioactive isotope here also. So during this process, we're converting mass into energy, which is actually like the next section, I think. It's called 8.6. Is the mass defect. Yeah, so that's the mass energy equivalence kind of formulas. If you're interested, take a look at it. But through this process, a neutron interacting with a large nucleus, we create two daughter products. We have three neutrons that are products to this reaction, and energy. And if you look in your data book, I don't think I have the equation, no. If you look in your workbook, sorry, they show the like nuclear equation there, and it shows that like 235 uranium, this is just its atomic number down here, collides with a neutron. That's our nuclear symbol for a neutron. One nucleon, no charge. We're creating the following elements. So we have 141 barium. 36 is the atomic number. Krypton, 89 mass, and 56 for atomic number. And I have three neutrons. And it also shows me that I have 200 mega electron volts of energy. So that would be like the amount of energy released for one fission reaction. Fission is the reaction that's used in like nuclear reactors and nuclear bombs. Now, those are, one is a controlled version of the reaction and one is an uncontrolled version of the reaction. So since it takes a neutron to get the reaction going, and it creates neutrons after, the neutrons that are products can then go ahead and interact again with a new uranium isotope or atom and continue on the process. So that's what I'm discussing when I'm saying like the emitted neutrons strike more atoms, causing them to undergo fission. So it's a big chain reaction. So you're using a neutron up and you're creating three in each fission reaction. So in that chain reaction, neutrons released from one fission reaction go on to initiate further reactions, which is why it produces so much high energy. And if it is uncontrolled, it's very, very dangerous. So an uncontrolled fission reaction is like an example of a nuclear weapon. So it's not controlled on purpose. It's supposed to produce very high amounts of energy and devastation. Whereas a controlled nuclear fission reaction is what would be happening in a power plant. So the way that we control a fission reaction is we have to have something extra in the system that absorbs those extra neutrons. So the neutrons that are coming out as products, they don't just have the opportunity to go ahead and react with a new atom starting a new fission reaction. So some extra material or different material into the system absorbs those excess neutrons before they strike a nucleus, leaving only one neutron from each reaction to produce another. So it creates that more of a 1-to-1 ratio, so one neutron in, one neutron out. And therefore, it's not a completely out of control reaction. It's just an example of like an uncontrolled nuclear reaction. We see one neutron into the system producing two extras that can then go and interact with two more uranium atoms, producing two more. So it's just like a big chain reaction of system. Whereas here, if I'm showing my neutron path, we end up like losing a neutron every single time. So it's a much more linear path and would have a lot less energy to control. So nuclear power is actually like a very clean and useful form of energy. If you haven't watched the Chernobyl like documentary or like limited series, I guess is what it is, a limited series, not an actual documentary, on HBO. It's a really good watch. It's only 6 episodes, and it goes into a bit of the science, and it's really interesting to watch, just to kind of hear the story of what actually happened through that entire event. But so if you haven't watched it, I would suggest it, and you can learn a little bit more about nuclear power through there. Our outcome isn't really focusing on nuclear power, but I think it's important to understand like kind of what the basic premise of nuclear power is. So obviously we're originating this from a fission reaction. So we're splitting uranium with neutrons through fission. And the energy that's released in that reaction is heat that heats up water to produce steam. So realistically, we're using like steam generators and turbines to actually like produce the electricity. The nuclear energy isn't just like directly into electricity in one step. We are using like steam generators to produce that electricity. So there's no fuel at all. So there's no greenhouse gas emissions, which is why they are like one of the cleanest and most efficient forms of energy like on the planet. They're just not always sought after by communities because not everyone wants to live near a nuclear power plant for reasons such as disasters that have happened in the past. But when they are controlled, they are very safe and very clean forms of energy. Okay, just a little background on fission. Now let's talk about fusion. So nuclear fusion is easier to remember because fusion is like we are fusing two things together. So the combination of two small nuclei to make a heavier element. The energy that's released due to the binding energy per nucleon, which is something from the next section, is because the binding energy per nucleon is greater than that of the original nuclei. So the energy when they bind together, there is energy released in that. So fusion is what powers like the sun, stars, hydrogen bombs, huge amounts of energy. And there hasn't really been, I guess, a lot of success in controlling a fusion reaction on Earth. So that's all still experimental. We haven't been able to like harness that huge amount of energy currently. So in the book, they show the reaction for hydrogen isotopes reacting together. So 2 hydrogen nuclei they're showing here. So tritium is this example right here. Its nuclear symbol is this. So it's hydrogen with just like 2 extra neutrons, so it has 3. And then deuterium, this is other isotope of hydrogen. So this is also the example in the workbook. I think those are just important isotopes of hydrogen to be familiar with. Deuterium is something you use a lot in like chemistry lab to like dissolve. It will dissolve like basically any substance, and it's really anything can be stable in it, I guess. So it's used for like NMR kind of imaging. So tritium and deuterium are 2 isotopes of hydrogen. And as they bind together, we are producing a helium. So I'm just kind of, maybe I'll just write out the equation here. This is the same equation that's shown in your data book. This is just the picture version of it. So we're adding 2 small nuclei together to make something bigger. So I'm producing helium. And we're also releasing a neutron. And we're releasing a bunch of energy. 17.6 mega electron volts, to be specific, is the amount in that reaction from our data book. So let's just go through a couple examples. So they're asking us to write out the complete fission reaction for uranium-235 hit with a low energy neutron. So uranium-235 Just need my periodic table here. Uranium is number 92, and it's hit with a neutron. Reminder that the 1 is here because the neutron has 1 nucleon, the neutron itself, and no charge on the bottom. And we're assuming what it's going to produce. They tell us in here to produce barium-141. This actually might be like the same reaction we kind of talked about already. Barium-141. So I got to look up barium on my periodic table. That's number 56. Krypton, 92. And krypton's atomic number is... Oh, I don't know where it is, actually. Oh, 36. It took me way too long to find. Our rules have to be... so our conservation laws have to be followed here. So we need everything to equal out. I can see that in the bottom line, 56 plus 36 does give me 92. I'm looking to make 236 up top. So I have 141 plus 92. That gives me 233, so I need 3 more nucleons up top, which proves to us why fission reactions also produce 3 neutrons separately. So that conservation law shows me here that 1 times 3, so there's 3 nucleons. So 141 plus 92 plus 3 gives me that 236 to make left side and right side equal to each other. Okay, in B, it's asking me just to explain how this reaction provides energy. This is actually something from the next section, but just so you know, the energy is supplied whenever we convert, it's basically converting mass into energy, and the formula that converts mass into energy is a formula probably all discussed before, but you've never actually used a lot of information or used to calculate anything. But E equals mc squared is a formula that we can insert a mass amount and we are outputting an amount of energy associated with that. And that would be what we would talk about in 8.6 had we be doing that. The important thing for here is being able to, for the most part, identify that this is fission. Okay. Next example, they're just asking us to write out the fusion reaction, and this is like the same reaction I just did. So deuterium is a hydrogen 2 isotope. Tritium is a hydrogen 3 isotope. Oh, we are making helium. And I just need to make sure both sides are balanced. So I need 5 nucleons up top, so that's where my neutron comes into play. And the bottom charges are all balanced. And for B, it's the exact same thing. E equals mc squared. We are doing a mass energy equivalence. Okay, there's only 5 little questions in this section. So basically it's asking you to go through, asking you to write a couple reactions, maybe even do a half-life equation for a fission and fusion reaction. And what I'm looking for your summative is just to be familiar. If I give you a reaction, can you identify that it's fission? Can you identify that it's fusion? Tell me a little bit of the difference between them and what ones are used in like nuclear reactors. So just knowing that fission is the one that's used in nuclear bombs and for energy. So let's just do 1 through 5 on page 130 to practice.